So hello, in this video I wanted to inspect how a Zener diode can help with a voltage divider, first in theory. I went to real dry run in theory because I have not practically tried this out, but then we'll see how our considerations would go in reality and if something can be predicted or not correctly. So let's start. So the big topic here is we want to do a voltage divider with a Zener diode. Well, that's the goal. So let's do some kind of neat formatting here. And for that, I'm putting up a Zener. The symbol should be along the lines of this. Then we having a resistor here, and up here we're having our, let's say, our 9-volt rail here, plus 9 volt, and here below we go down to, let's draw this a little bit further, this line, we go down to ground. So 0 volt. And the theory about the Zener is that it depends on which Zener diode you have. So I have in my toolbox, I have a 5.6 volt Zener. And then I don't know what kind of resistor to use here. Let's just make it 1K kilo ohm resistor, and then of course 9 volt, 1K, 5.6 volt over the Zener. How much voltage is over the 1K resistor? It is 9 minus 5.6. So the Zener has here 5.6 potential, so that is also what is at our output, 5.6 volt. But that's really the clue about the Zener. It takes care that across it always there is this certain voltage. And through the 1K resistor we drop 9 minus 5.6, that is 3.4. So we have 3.4 volt across the resistor, and that leads to 3.4 milliampere also, 3.4 milliampere across the resistor. And yeah, so that's the basic setup with the Zener diode, 5.6 volt output without a load. And now let's see what would happen if we would connect a load up here. So let's say here now this resistor. Let's make it again somewhat 50 ohms. 50 ohms. And let's imagine what would happen. So the Zener diode, it would take care that the voltage across this is 5.6 volts. So, and in a parallel circuit, the voltage must be equal over the whole parallel branch. So expect still to be 5.6 volts here. And if you have 5.6 volts over this 50 ohm resistor, then we can calculate the current. Current equals voltage divided by resistance. And if we divide 5.6 by 50, that gives us 11.2 milliamperes. Oh no, it's 112 milliamperes, really, sorry, 112 112 milliamperes. Okay, that's a lot. I mean, again, this 112 milliamperes, they have to come out of this point here, and this 112 would go through here, and also additionally some amount of current would go through here. So we have leaving in this and this direction at least 112 milliamperes, but also these must then come in through up here, and that is not quite in sync, because we said having 5.6 volt here, there must be 3.4 milliampere through this resistor because of the 3.4 volt different, 0.4 volt different here. And I really wonder what would happen here. Then what would happen here? Because if we would really have 112 milliampere through here, and then we would have 112 milliampere across the 1K resistor in this scenario. So 112 milliampere at least, and then across through this resistor, and then we would have 112 volts across this resistor, and that clearly cannot be. And yeah, so either the voltage here is not 5.6 volt in the scenario then, so that means the Zener can't keep up the 5.6 volts, and this is going to be a simple voltage divider. Or what else could happen? It could happen that we have not more than this 3.4 milliampere, that this resistor is flown through at maximum 3.4 milliampere, and then what would happen? 3.4 milliampere through 50 ohm resistor. This would be 170 millivolt maximum across this 50 ohm resistor then. Lots of funny scenarios what could happen here. What do you think? You also can post me in the comments. I wonder if I should try this out practically, because it's 112 milliampere. If this really blows, then something could blow up here. Hey, but let's be brave. Let's hook this up and let's see what we get out here. So that's the setup situation. We have here positive rail. We go through the resistor, then to this point here in the middle, and then through the Zener to ground. And before the Zener, I have this yellow wire attached, which then I measure with this little pin here on my multimeter. What is the output voltage here in the middle? At the moment we have no load connected, so this should go pretty well. So let's switch on the power source. I have made it a 9 volt power source like we drawn it, and I have my power source can limit the current, and I have limited to 100 milliampere. Just things don't go completely wrong, and watch it, because my power source also, it can tell you how much current is flowing at the moment out of the power source. This will be a helpful measurement also. So I switch the power source now on, and let's see how the multimeter behaves on the output pin here. At the moment we're reading 13.7 millivolts, some irrelevant ambient voltage, whatever. So I switch it on. And we're measuring a good 5.56. So 5.5. The nominal Zener value is 5.6, and that's good. That's okay for a Zener. I bought a bunch of Zeners just with no quality assurance checked from my side, just a random maybe Chinese package of a collection of multi-value Zener diodes. Okay, Yeah, and now the most interesting thing comes. We are going to connect up a load on this thing. And then we wonder what kind of voltage will be there at the output. And so I connect it to ground and then to the output. And let's watch what happens at the multimeter. We're going down to 405 millivolts, and my power supply says it's driving around something around 5 and 8 milliampere through the thing. So all in all, seen from positive rail to ground, the whole current is around something from 4 to 8 millivolts. And of course, this whole current must go through this this resistor here. So we're very stable at 405. Yeah, and let's go back with these measures. Perhaps we write them down also a little to remember them. So we said we have 405.9 millivolts across the second resistor, 5.9, and we are around at at something between 5 and 8 milliampere. I measure this more, I think I'll measure this more direct with another multimeter. And for this, I connect this resistor up to here. And then we have here the second meter. I put it to milliampere. 200 milliampere must suffice. And we connect that up again. Yeah, we're going around to approximating our 405 millivolt again, and then we have very clearly 8.5 milliampere flowing in to the upper resistor here. So I note that down. Resist or U, I abbreviated for upper resistor. 8.5 milliampere. And then I would be interested what flows through the lower resistor, but yeah, we can tell because of the millivolts across the resistor. We can tell what flows through the resistor, and then we can logically derive what must flow through the Zener then. Okay, that's the setup. Let's go back to theory. Okay, back to theory. We have seen that really we have not 5.6. When we load this circuit, we have not 5.6, but we have really have only 405, I rounded to that, 405 milliampere across here. So that 170 millivolt was also not millivolt, sorry, millivolt. 405 millivolt across here, and we measured that there is flowing in here 8.5 milliampere. And let me calculate that. Then that means that across this 1K resistor there is dropped around 8.6 volts, 8.5 volts. But as we see here, most probably there was a significant digit there that we did not get on the scope on the digital multimeter. Most probably was more like in the 8.6 range. So if we drop this 8.6, then we end up with this 400 millivolt here, then, so to say. And then if we calculate roughly with this 400 millivolt across the 50 ohm resistor, 50 ohms here, and this for, yes, let's say 405 millivolts across here, what current is that? It's 8.1 milliampere across the resistor, and only about what is left then for the Zener diode. Yeah, it's around 0.4 milliampere left for the Zener diode. So that is equal to 400 millimicroampere. And somehow this does not then suffice to keep up the reverse bias of the Zener. Okay, so somehow if we put a resistor in parallel to the Zener, you can't keep up the 5.6 volt, so it breaks down. That's an interesting thing, because it tells us that the voltage divider with the Zener is not suitable for driving loads that need much current. The Zener will then somehow break down. There will be only no more 5.6 volts, what the Zener is designed to do, and most of the current will go through the resistor, then to the load. Interesting. Okay. So, but what the Zener is very cool at is, if we manage with a technique that we also seen in another video with a BJT transistor we did it, we managed to stabilize the output here, because we get the current then from somewhere else, and we don't have to draw the current through here, but with the transistor we get the current then from here through this path. When there is here sitting a transistor, we've seen that already. Then the Zener has the property that if I go lower here on the 9 volts, so perhaps I've seen 8.4 volt, for example, on my batteries, or you can even go down to what, I don't know, 8.1 volt or even lower, then the Zener has the property of keeping the voltage here stable. And that is a very cool thing. And I'll do the next video about this to prove that in practice, how this voltage here is kept stable by the Zener. If we do something here about the current, that the current is not flowing through here, through the load, through this pot, but coming from somewhere else. Okay, thank you, and until the next video.